In the last section, we talked about relations and we talked about different terminologies we could use to say that two elements are related to each other. So we said A is related to B. We said A R B, where capital R is the name of the relation. We also said AB, the ordered pair, is an element of R. And in the background, we initially said that A and B could possibly be from different sets. But for the purposes of this section, we're going to say that both little a and little b are elements of capital A. They're elements of the same set. And we're going to say that capital R is a subset of A cross A, the Cartesian product of A with itself. Remember that we had an alternate notation for A cross A, which is A2. We don't say A squared, we say A2. Kind of like when you say this, you write it this way and you say R2, you don't say R squared. Now, there's an important notation that we should consider when we're talking about relations, which is this notation that was kind of talked about in the last section, but we're going to use it a lot more in this section. So we have that the ordered pair A comma B is an element of the set of ordered pairs XY in A cross A such that X is related to Y. So this is just a quick review of the terminology we need, but it's also reminding us that we need to frame it in terms of A cross A rather than A cross some other different set B. The goal is to talk about properties of relations. Now there's a quick typo that I fixed. You'll see it in a moment, but the way we're framing this is R is a relation from A to A. In other words, R is a subset of A cross A. And we say R is a relation on A. Instead of saying R is a relation on A and B, there's just one set, which is A. And if you think about some of the homework problems from 7.1, I believe it was number 6 and number 7, they kind of have you play with that idea of a relation being on one set. When we have a relation defined on a set, we can think of some properties that that relation has. So we say a relation is reflexive if every ordered pair where both coordinates are exactly the same thing is in the relation for all A in A. Irreflexive is the extreme opposite of that, meaning there is no such ordered pair of this form in the relation. Symmetric means A is related to B implies B is related to A. Remember, in general, in the last section, we saw that that's not always the case. So for every pair AB in the set A, this if-then statement is true. Antisymmetric is one that takes some getting used to, but we'll work through some examples. If the ordered pair AB is an element of R and BA is an element of R, implies that A is equal to B. So we'll work with that one definitely, because it needs more explanation than that. Transitive is A is related to B and B is related to C implies that A is related to C. For every possible situation where this occurs. Now I want to just go over these one more time, but with the slightly different notation that we've seen. Okay, remember we're going to see this notation a lot, the capital R being between two elements. So reflexive is ARA for all A and A. Irreflexive if A is not related to A for all A and A. ARB implies BRA is symmetric. antisymmetric is ARB and BRA implies that A and B have to be equal to each other. And then finally, transitive A related to B and B related to C implies that A is related to C. So because of the extreme opposite nature of the definitions for reflexive and irreflexive, it's impossible for a relation to be both of those at the same time. If a relation's reflexive, there's no way it's going to be irreflexive. And if it's irreflexive, there's no way it's reflexive. It's also possible that a relation is neither reflexive nor irreflexive. And I know you might be thinking about symmetric and antisymmetric. Those are not exactly opposites, and we'll get into that more right now. So let's talk through that. It actually is possible for a relation to be symmetric and antisymmetric at the same time. Remember, antisymmetric has a very specific definition that we just mentioned, and we definitely need to practice with that idea to understand why they're not exactly opposites of each other. It's also possible for a relation to be neither symmetric nor antisymmetric. Okay? Let's think about what the contrapositive is of the definition for antisymmetric. The contrapositive would say, if A is not equal to B, then it is not the case that A related to B and B related to A happens. So antisymmetric tells us if we have two distinct elements, distinct is coming from A not equaling B. If we have two distinct elements, A and B, that are related, we either have that A is related to B or B is related to A, but we don't have both. Think about what the negation of this and statement says. It actually amounts to what's written here. So if we can find distinct elements A and B where the ordered pair AB and the order BA both belong to R, then we can rule out saying that the relation is antisymmetric. Let's look at some examples. We have the relation R on the set A. Remember, we only need one set right now because we're talking about these properties on relations on a single set. So R is a relation on the set A, which is 1, 2, 3, 4, defined by these ordered pairs. Remember, relations are always sets of ordered pairs. We can always think of them in that way. So what you'll notice is we don't have 2, 2, which tells us that this relation is not reflexive. Remember, you have to have every possible pair A, A in your relation in order for the relation to be reflexive. And then it's not irreflexive because we do have some ordered pairs of the form A, A. Now, because we notice we have 2, 3, if this is symmetric, we're expecting 3, 2 to also be in this relation, and it's not there. So R is not symmetric. Now, if we take any distinct elements of the set A, we notice that, like, for example, 2 and 3, if we have the elements 2 and 3, we have 2, 3, but we don't have 3, 2. We have 2, 4, but we don't have 4, 2. We have 3, 4, but we don't have 4, 3. And we don't have any that start with 1 except 1, 1, so we don't need to worry about that. But for every ordered pair that consists of two distinct coordinates, we see that only one of these 4 possibilities happens, and that's what tells us that R is antisymmetric. So what about transitive? When we go through the ordered pairs in R, we want to check 2 is related to 3, 3 is related to 3, so 2 is related to 3. Is 2 comma 3 in the relation? Yes. Okay, that maybe was a silly one. 1 comma 1, well, there's nothing that starts with the ending point of this ordered pair, so there's nothing really to check with this one. And there's nothing that starts with 4 either. But this definition here is being satisfied in an empty way. Remember, the if-then statement that is the definition of transitive will be true if the premise is false, right? Remember the truth table for implication, right? The only time we have false for the implication is if P is true but Q is false. Okay, so when the premise is false, in other words, when A comma B is in R and B comma C is in R is not true, the if-then statement is true. The promise is fulfilled. So it actually turns out that this relation is transitive. What about this relation? There's only 2 ordered pairs in this relation. There's no ordered pairs of the form A comma A, so that means this relation is irreflexive. And it's definitely not reflexive. It's the complete opposite of reflexive. Now, we only have to check what's going on with 2 ordered pairs. So if 2, 3 is in the set, then 3, 2 is in the set, in the relation. That's true. If 3, 2 is in the set, then 2, 3 is in the set. That's true. That means S is symmetric. We have 2, 3 is in the relation, and we have 3, 2 is in the relation. So the premise of the if-then statement that gives the definition of antisymmetric is true. The premise is true, but the conclusion, 2 equal 3, is not true. So because of that, S is not antisymmetric. And then finally, if S were a transitive relation, then having 2, 3 and 3, 2 in the relation would mean we would have to have 2, 2. In fact, it would also mean that having 3, 2 and 2, 3 in the relation would mean we have to have 3, 3 in the relation. And we have neither of those in there, so that tells us S is not transitive. So the only properties that this S has, according to what we've just examined, is that S is irreflexive and symmetric.